Okay, we'll discuss today a few problems that are listed in the lecture number 8. So this is the part of the lecture that is with a bunch of problems that are using calculation by way of permutations and combinations and efficient counting, and then answering some problems in terms of probability and so on. So first problem, we're going to do this problem that is about the arranging 5-passenger and 7-seat van. So there are 4 rows of seat, and this would be arranged in a way that we would have 5 passengers, 7 seats. In the first row there are 2 seats, and one of them is for driver, so you're not going to be able to put anybody in that place. So this is what it will look like. 7-seat van. I'm not making a great picture, but this is really not important. So I have the first row of seats. One of them is for driver, so that is not for passengers. And then we have 3 more that will be for passengers. So you have 7 seats for passengers. And I'm gonna call a row to be the vertical setup, like this is one row, this is another row, this is another row. Okay, so if you are arranging seating for 5 passengers, you have now many different ways to do that. And if you have a 5 passengers, then you have to ask yourself, can you possibly write it down? So if it's a random arrangement, and the answer for that would be that this time it's not possible. This is the sample space of all the possible arrangements you can have. It's not possible to write down, and so you have to find some better way to do that. And of course, we're going to use now the story about combinations and permutations and arrangements when some number of things is available, and then we're selecting some number of things from that available set. Now we have the 7 objects to choose from. We are selecting seats, of course, not a passenger, but seats. You have 7 objects to choose from, and you're selecting 5, and you will assign them to passengers. So, for example, in this group of passengers, I can say we have, let's say, Bill. I'll pretend like I have some names here. John, Matt. I'm going to use all male, but it doesn't matter really. Fred. And what else can I do? The Pat. Right? So I can assign seats like that. Bill, John, Matt, Fred, and Pat. Okay? Now once you realize that you're selecting 5 of the 7, so you immediately know that this is going to be one of those selections we have in the table. We have formulas for it. You're going to ask yourself, do you have repeating selections? So can you have now this seat for Bill and then the same seat for John? Of course not. So there will be no repetition. And then you ask yourself the second thing, does the order matter to you? And the order matters. And let me argue that. So if you have a Bill here and Pat here, Pat might not like it. Maybe he wants to sit in front. Maybe Bill doesn't like to sit in front. Maybe he wants to sit somewhere else. So the order matters. So again, you have the same seats for Bill and Pat. But if you do that in this way, they put Pat forward and Bill back, then you have different arrangement. And I think these 2 guys, for the rest of them won't matter, but these 2 guys will definitely see that as different arrangement. And it is different arrangement. So the order matters. Which means you're dealing with permutations. We are talking about permutations when 7 chooses 5. This is a rather large number, so you can calculate that number using either formula. We have the formula that is available to us, which is, so you have a 7 factorial on the top, on the bottom, you have, for permutations, you have 2, you're not choosing 2, so 2 factorial on the bottom. That's how the formula goes. Obviously, you certainly use a calculator, and I mean, this is a good place so you can see the advantage of having a good calculator. And if you use a calculator, you're going to have 7. Then you go math, you look for the probability, and you look for permutations. And now you have to also write 2. 7 chooses 2. And that's going to be now by, 7 chooses 5. Excuse me, my mistake. Again, I forgot already, I'm 5 passengers. I need the seats for 5 passengers. See, if I have just 2 passengers, I only have 42 options. Interesting. So, but I have 7 math, and I have to select the permutations 5. Now that's a huge number. So to arrange the seats for 2 passengers is much easier than this. So this is 2,520. Okay, 2,520. All right. Now the part of the problem says, the second part of the problem, the B part, you have 5 of those passengers, and 2 of them are John and Bill. They cannot be seated in the same row. For some reason, they don't like each other, so you can't put them in the same row because you're going to have some problem. Okay? So the question is, how many arrangements we have with this restriction that they cannot be seated in the same row? All right? I'll first answer the question, in how many ways I can seat these 2 guys in the same row, right? And that's an easy answer. Okay, I can put them here in the same row, John and Bill. I can also reverse this. I can put Bill here and John on the bottom, so I had the 2 different ways just for this row. And I have 2 different ways to put them here, and I have 2 different ways to put them here. So basically, the B part of the problem. So this is the B part of the problem. I have 6 different ways to put them in two seats that would be in a way that I don't want to have them. Okay? But that's not all, because I definitely have to put the other 3 guys somewhere. So I can put them here or any other way. So for the other 3 guys, I need to find 3 places, and that's going to be permutations, just like I was doing the moments ago. It's going to be permutations in which I have 5 available seats. Once I have seats for John and Bill, and in those 5 available seats, I put 3 people. So my first choice is where to put John and Bill in the same row, and my 6 ways. And my second choice is where to put 3 other people in these remaining 5 seats, and that will be 5 chooses 3. So this thing here is 60. It's a huge number. I mean, huge number. It's not a huge number, but it's a big number. In which way I can put 3 people in 5 seats, and this of course is still 6. Yeah. So I'm getting here 360. So I'm having a 360 different ways where I can put Bill and John in a way that we should not have them. Okay. Now, if you're interested in probability, you might ask, what happens if I randomly select seating arrangement? So just like drawing out a hat, the seat number 1 for John, the seat whatever I'm drawing out the hat for Bill, in that order. I can put them Bill, John, and then whatever I'm drawing out the hat for Matt, whatever I'm drawing out the hat for Fred, whatever I'm drawing out the hat for Pat. Okay? If I do it at random, they're all equally likely. Any arrangement is equally likely. And 360 of those arrangements are not eligible, and the total number is 2,520. So the probability of problem, we can call it that, probability of a problem, right? I don't want to write all of that. The probability of having a Bill and John in the same row by randomly selecting seats. Probability of a problem. Probability of a fight during the transportation, right? I didn't say that that's the problem, but let's just say this is not possible to do. We can't do that, because we're going to have a problem. So probability of a problem is going to be 360 divided with the, I don't know, 2,520. That's what we calculated. All equally likely. 360 is with John and Bill in the same row. And we have this old formula we had some time ago. This is not going to be calculated precisely, but I can get this done. So we have 360 divided with 2,520. So I get 14%. So the chance of that is, according to my calculator, dividing this, I got about 14%. So I have 1 out of 7 chance to get trouble if I don't pay attention that this cannot be done. Now, if I want to eliminate the problem, then I have to eliminate 360 possible arrangements with Bill and John in the same row from this total number. And the answer to the problem, the part number B, is that we have 2,520 minus 360 eligible seating arrangements. That would make it to 2,160. Okay, that's the answer to this problem. Okay, let's go another problem in the lecture. Says this one here, number 2. If we are going to assemble a committee out of 5 people from a department which has 7 mathematicians and 5 physicists, and Dean decided that he wants to have 3 mathematicians and 2 physicists because they're kind of proportional selection. In how many ways he can have that, right? So here's the story is about the 2 choices. The first choice, so it's problem number 2. The first choice is in how many ways you can get mathematicians, and the second choice is how many ways you can get physicists, right? In the first, you have to choose 3 out of 7. Okay. Now the question is, you have 7 available objects, mathematicians, and 3 that you have to choose. You cannot repeat, so you can't have Bill, Bill, and Bill. Had to be 3 different people. But the order doesn't matter to you. And the order doesn't matter because it is not ranked. Nobody said that this is a first person in the committee, second person, or some ranking member, or chair, or stuff like that. No, they're all equal. So nobody said that there's a difference here. So you have to have, you are going to have the combinations. The order is not important, right? So this is in how many ways you can get mathematicians. Now you calculate this by using formula. You can just simply use a calculator. 7 chooses 3. I think that goes to, I believe, number 35, but I'm not so sure. Let's just be careful. So I have 7, math, probability, combinations, 3, got 35 indeed. So this is 35. Okay. So there's 35 different ways you can get 3 mathematicians in a group of 7. Each one of them is applicable to be in the committee. Now, you have the same problem with physicists, only you have now 5 available, and you're choosing 2. So you can use the same reasoning. Now, this number is much easier to calculate, it's 10. So in 10 different ways you can get 2 physicists out of a set of 5. So you have to multiply this because it's a branching over 3. Any selection here you have combines with any selection here you have. Any selection of mathematician with any selection of physicists. So you have 35 different ways to get mathematician, 10 different ways to get physicists, and the total number of ways you can get, this is like a 3 branching. So first, mathematicians, then physicists. You have 350 different ways. 350 different ways that you can get this committee done. Okay? Notice this is important here to notice that we have committee that is not ranked. So which means that we have the combinations, we don't care about the order. Now, if you have to select a ranked committee, in which case you're going to have maybe something like a chair, vice chair, secretary, stuff like that, then the order will matter. Okay, let's go for another problem. I'm playing poker in how many ways you can get 5 cards. Oh, that's an easy one. Again, you have 52 cards. You're gonna select 5 at random, right? And how many ways you can get that? The repetition is not possible. The 5 cards must be different. The order doesn't. You don't care about the order. You get the Queen of Spade and King of Hearts first and second, or you get the King of Hearts and Queen of Spade first and second. Makes no difference to you. You can rearrange them anyway. So this is definitely combinations. Now you can use your calculator, and your calculator will tell you that total number here is 2,598,000. It's a large number. And 960. Okay. And I reasoned that here by using formula here, but of course you can use a calculator. It's much easier to do that. Now there are lots of interesting questions here. I'm not going to answer most of them. I'm going to leave it to you. How many ways you can get the one pair of a kind, which is the most often thing you get, like a 40. The story here goes on that you can get about 40% of the time. So if you take a random 5 cards of the deck of 52, there's a 4 out of 10 chance that you're gonna get one pair, and nothing better than that. Just one pair, any kind of pair. It's also about the same 40% of the time you get nothing whatsoever. There's no value at all, like a just lousy hand. Okay, there's a more interesting question in how many ways you can get 4 of a kind. Now 4 of a kind is easy to calculate by multiplication principle. The story goes on that you will have the I don't have enough space here. I left something open here, so we're going to the top. So the 4 of a kind, which means that you need to have 4 of a kind and the 5th card. So the 4 of a kind you can take out of any denomination, so there are 13 possibilities. And then once you take the denominations, it'll be 4 aces. For example, you could have, I don't know, 4 jacks, and you can have 4 queens, so you can have 4, I don't know, threes. Strong hand anyway. Now you need to have a 5th card. The 5th card is not going to be out of those 4, right? So it's going to be something else, and you have therefore 48 possibilities to get a 5th card. Okay, this number turns out to be 624. So there's 624 different 4 of a kind. Okay, it's a huge number in terms of if you need to write it down, what all the possible chances are. That's a pretty big number to write down. Now, obviously you can get these. Now the probability of getting 4 of a kind is kind of easy not to get. So probability of 4 of a kind. You have to divide this number down upstairs. There we calculate 624 with all possible 5 card hands you can have. So this is now that formula we have for the probability that says the frequency of event, which is in our case 624. How many possible 5 cards hands you can have? You can have 2,598,960. And this is really going to be very rare. The chance of getting 4 of a kind is going to happen 624 times out of 2,598,960 times. And if you want to have the percentage wise, you're not going to get even 1%. It's going to be something really small, but you can definitely divide that, and you get. I'm dividing. I didn't turn the calculator on. All right, so let me try again. So 420 624 divided with 2,900,500. The number is so big that I forgot it what it is. And now you got the, oh, this is, it had to be on the 4 decimal place. I'm just write it for you. So this is the, I'm gonna put a wiggle here. It's not exactly equal. So, and I have 0.00024. That's what it is. Approximately. All right. This is an approximation with 5 decimals, not a bad one. Here is the place of a percent, so it's 0%, and you can say this is 2 places further. This is a 2% over 1%. A little more. You can say 2.4% over 1%. Okay. So this is the chance of getting a 4 of a kind. Okay. We can ask more questions here, like in the lecture is what is the chance to get the 1 pair of a kind. You can read that. I wrote some something about it. Then let's do this one I didn't write. This is really tricky one, the last one. I'm going to leave it to you. You can find the stuff actually on the internet, because the internet has these things. I think this last one, getting 2 pairs, is about 5% all the time. But getting a full house, now we know that's a weaker hand than the 4 of a kind, and it's weaker because it's more often, right? The weaker hand is more often, so that's why it's the weaker hand, and that's how the rule of the games are that way. So you can, something that is much more often is not as strong as something that is rare. And so full house, we know how to do that. Well, let's see. Okay, so I got to think the same way. You have to make decisions. So your first decision is going to be to get a full house in how many ways you can get 3 of a kind. Okay? First of all, you need to decide what denominations you're going to use. Maybe you can use aces, maybe you can use 3s, maybe you can use, I don't know, queens, maybe you can use 10s, but you have 13 options. Now once you select that, you still have 4 cards, and you need to have 3 out of those 4, not all 4. So in how many ways you can get 3 out of those? Let's say you selected aces to be 3 of a kind. Aces to be 3 of a kind. Now you need to find out in how many ways you can get 3 out of 4 aces. Obviously, you're not going to repeat, so you have 3 different cards, but you're also going to, you will not care about the order, because if you get ace of spades, ace of diamonds, and ace of hearts, it's the same as ace of diamonds, ace of hearts, and ace of spades. So the order doesn't matter to you. So these are combinations. So your second choice is what 3 out of 4 aces. Okay? So we're going this 3 branching like we had with that pizza story, that restaurant story. Now, once you have a 3 of a kind, so this is all for 3 of a kind. You select the denomination, aces, then what 3 or 4 aces, right? Now you have the 2 of a kind. You are left with 12 possible denominations. You can't have aces and aces. Now you're going to have to set something else. And let's say you have 10s. So now you have selected 10s. You could have selected anything of the other 11. So you have 12 the options there. Now you need to select what 10s you want, because there are 4 of them, and you need to select 2 of them. So by the same logic like we had moments ago, we are selecting 2 out of 4 combinations. Again, the order doesn't matter which 2, but they have to be 2 different, so the repetition is not possible. So now this is the story here. So you have a 13. This number here, you can use your calculator, is 4. This number, of course, there is 12. And this number here, 4 chooses 2, is actually 6. Again, use your calculator or use the formula for combinations. But you can get one way or the other, 6. Now, when you multiply all of that together, you get 3,744, which is actually coincidentally, or maybe not so coincidentally, 6 times this number. So you multiply 624. My calculator goes off batteries all the time, right? So if you multiply 624 times 6, you get 3744. So which means that the full house is 6 times more likely and more often than 4 of a kind, which also makes the probability easy to calculate, because now you just have to multiply this probability with 6, or you can just simply do the same calculation I did moments ago. So I have full house I get really annoying phone calls every 20 minutes. Alright, so I have 3,744 divided with 2,598,960, and that number is, according to my calculator, something small, but it's a better chance than having the 4 of a kind. And what the calculator says, this is maybe possible. I'm gonna have 4 decimal places enough. My calculator says this is 0.0014. Now this would be a 1/7 of 1%. So which means that if you randomly select 5 cards out of the deck of 52, you would have you have to do that 700 times. Then maybe you can get once full house. Okay, so it's very rare, and it's a very strong hand, so you usually win with that hand if you ever get it, but it's very rare. However, it's a lot more often than 4 of a kind. 4 of a kind is impossible to see. I mean, it's really not going to happen very often, and if you do that, you can deal the cards, 5 cards out of the deck of 52 whole day, and you might not see it at all. So this is basically, not like in the movie, which in every movie, whenever there is a poker game, you will always see 4 of a kind, but it's not going to happen really that often. And as a matter of fact, 2 pairs is very strong. You can really win with 2 pairs. 3 of a kind is definitely going to be a good winning hand. And full house is rare, so you can see that there's not a great chance to get that. Okay, let's do something else here. This problem number 4 illustrates the way you can calculate by using both Combinatorics properties of probability, property of probabilities that we listed 1 to 6, and using counting. Okay, what's the story? It says, if you're selecting 2 cards at random, what's the chance that both of them are spade? And I'm going to calculate that in a very simple manner by using Combinatorics properties of probability. Okay, so when you say probability of both spades, 2 cards. So you're drawing 2 cards at random from a deck of cards of 52 cards. What is the chance that both cards that you are drawing are spades? Okay, you can even play this game with somebody. Usually people think this is much better probability than actually it is. So you can, you can play him against somebody who thinks that he can get 2 spades, and he's not going to get that very often. It's going to happen 1 out of 17 times. This is not a very good probability if you want to bet on that. Okay, it's rare. Okay, now how do I know that? Okay, first of all, if I use a Combinatorics property probability, I can divide this into 2 events. I can say the first card is spade. I'm going to write it like this. The first card is spade, and the second card is spade. So I'm going to write like this. The second card is spade. Okay? Now, we can call this A and B. And this will remind you on the Combinatorics properties in which we are trying to find out what is the chance of getting the A and B? And you remember this property number 5 and property number 6. The property number 6 actually is the one. The number 5 just follows from number 6. But the property number 6 says two events are in either way, but we wrote that dependent. But these are dependent events. Because if you take the first spade out of the deck of cards, the chance of getting first spade is 1 out of 4. Because there are 13 out of 52 cards that are spades. So it's 1 out of 4. Every fourth card is spade. But once you take the first spade out, you are left with 12 spades in the deck. And you have 51 cards. So now it's 12. The second card to be spade is 12 out of 51. That's less than 1 out of 4 chance. You can divide it, you'll see it's less. It's less than 25%. Simply because the first card was spade, so there's 1 spade left. One spade less. Well, you still have 13 clubs, 13 hearts, and 13 diamonds. So you have 12 spades. It's less than 1 out of 4. So this is dependent events. And we know for dependent events, we can write this to be equal to probability of A. So this is the property number 6 I'm using. Property number 6. That equation we had there. Time the probability of B given A. Given that you know that you have an A. Okay? So that's exactly the property number 6. I'm not really inventing anything here. Okay? Now that means the probability of having a first spade, which is 1 out of 4, and then, or 13 out of 52 if you like, 13 spades out of 52. And the second one is probability of getting second spade, which means that now you have the deck of 51 cards where you have 12 spades. So it's 12 out of 51. That's less than 1 out of 4, okay? Now these are to multiply two fractions, so it's really not that hard to do that. And I can cancel actually something to get a little bit easier to work with. Again, 3 here, if I cancel 4 and 4. So 3 out of 51, I still divide with 3. I divide this one with 3, 17. And divide 3, so I get 1 out of 17. Alright? Not a surprise, I already told you that's going to happen. So that's one way to do that. There's another way to do that. The question is, can we do that by efficient counting, which is kind of like I don't have to remember this property probability, which you should, because it's really important. But if you're going to do efficient counting, that's what you're going to have to think about it. How many ways you can get 2 cards to the deck of 52? That's an easy question because it's a similar question we already had. It's 52. When we were talking about the 5 cards, and we had the 52 combination chooses 5, but now you have 52 combination chooses 2, because you only need 2 cards. So there are how many ways you can have 2 cards of the deck of 52? So you're randomly choosing 2 cards of the deck of 52. What is really this number? Now the combination, so this is kind of like a big number. It's not really that hard to calculate. You can use a probability, the formula, which is what a formula says. On the top you have a 52, you have to make a factorial. You really don't want to do that because that's numbers you're not going to find on your calculator. Maybe you will, I don't know. And down there how many you're choosing, 2 factorial, and you also have to multiply that with the how many you're not choosing, which is 50 factorial. Sorry, lots of that get cancelled here. So I have only 52 times 51, actually 26 times 51. So one way or the other you can use your calculator. So that's 52. Math, probability, combinations, chooses 2, and calculator says it's really not that big number. Eventually 1326. 1326. So these are 1326 different 1326 different ways to get 2 cards out of the deck of 52. Okay? Now, in how many ways there can be 2 spades? Well, it's the similar question, only this time you're talking about spades only, so you have only 13 spades. And if you're choosing spades, so you look at how many ways I can get spades. You have 13 cards to choose from, and you will choose 2. So I get the same calculation here, only the 52 is now replaced with 13, so I have a 13. And down there, I'm still choosing 2, so that's down there, and the one that I'm not choosing is not 50 now, it's just 11, right? 11. So, okay, this is like 13 times 6, I think that would be 78 ways. Right? So now, if you want to answer the probability is going to be probability of both spades. And you know what? I'm just going to copy that one, otherwise I have to write too much. Lazy. Alright. Look at that. Alright. I'll write it here. Alright. Well, it looks like I didn't copy everything, so I'm going to add it here. And I will close parentheses here. Alright. So according to our good old theoretical formula, we have to, for that, how many you have in your event. You have 78, both spades. How many you have total number of outcomes, 2 cards, only 2 cards, 13, 26. They're all equally likely. And there's a finite number of them, 1326. Not a small number, but guess what? This is 1 out of 17. I'm going to show you that because I'm just going to simply divide 1326 with 78, which is easy. But I'm going to use a calculator, of course. 17. So this is indeed 1 out of 17. Not surprised there, because of course, there's a 2 ways to calculate probability. One of them we're using counting. This is the second way. And the first one was using properties of probability. Is a property number 6 I use. Okay, so you might want to check this out. You want to think about it. You need to really reconcile this with the property number 6. You need to make sure that you understand this property, how it's used here. But counting is also relatively easy, of course, if you know combinations. Okay, let me do one more. So I have the there's an interesting question: how many ways you can rearrange the word summer? Never mind the meaning. So this is one way, this is another way, or something else. You have 2 M, so this is a little bit of a problem. And you won't want to think about that. The Mississippi, in particular, you can rearrange the characters in the word Mississippi with lots of S's and lots of Y's and lots of P's in 36,650 ways, and maybe, I don't know, drop by my office, we're going to explain that, but right now I'm not going to write it. So let's see the number 6 here. Number 6 is a very interesting problem because it shows you again that you can calculate something by using counting, but you can also calculate something, the same thing, by using the properties of probability. I'm thinking about what I want to do first. I want to do the A part first. I'm going to leave that the B and C part to you. The hat has 3 white balls and 4 red balls. We are selecting 2 balls at random from the hat. What is the chance that both are red? What is the chance that both are white? What is the chance that one is red and one is white? The most often you're going to get 1 red and 1 white. It's going to be, I tell you that right from the get-go, you have more than 50% chance for that to happen. You have better chance to get both balls red because it's just simply there are more red balls. And you have the least chance to get both balls white. So I'm going to do the A part, I'm going to leave the B and C part to you. C part is explained here, so I want you to go through that reading. The B part you can do the same way I'm going to do the A part. It's only going to replace red and white. I mean, there are some numbers difference, of course. Okay, so this is the story. You have the hat. And in the hat, you have 4 red balls. And I'm not going to put any number on it. You can put number, you can call it red 1, red 2, but then it becomes story about permutations because you're going to have the number on the ball, so it will, it'll be different if you get the first ball out and red number 1 or red number 2. then you're gonna have a little more of a problem to work with. You can disregard that, but just simply say, I'm not gonna put any number on the ball, so let's just say 4 red and 3 white. So all of the balls are the same to me. They're just different in color, and I'm not going to be coloring here anything. I'm just going to keep them with the character W or R, and you guess what it is. Okay. The probability of getting both red. That's what I care about. Both red. I'm not writing everything, just both red. Okay. That can be again written as a probability of getting the first red and second red. And this is again that property probability that we just mentioned before. The number 6. And again, the reason why I'm using number 6 and not number 5 is that I'm actually here having the better than 50% chance that I'm going to draw the first ball to be red. Right? It's 4 out of 7 because I have 7 balls and 4 are red. But once the red is out, I have 3 reds and 3 whites. The second time I'm drawing the second time I'm drawing ball, I have a 50% chance to get red. 3 out of 6. It's not the same. Which means that the event first red and the event second red are dependent events, which again, according to the 6th property of probability, can be calculated by multiplying probability of the first event, the first ball to be red, time the probability of second event, given that the first event has happened. Probability of second being red, given that I know the first one was red. Okay, this is the property number 6. You can call this A, you can call this B, then this is A, and this is B given A. That's exactly what the property number 6 is. Alright, so again, you can call this first red to be A, you can call second red to be B, and this will be probability of A time the probability of B given A, given that A is certain. Right? The probability you're going to have the first ball to be red is 4 out of 7. Not really hard to calculate, right? You have 7 balls, 4 of them are red, it's 4 out of 7. Okay, the second question is now about this probability. Well, it's easy. If the first is red, that means like this one is out. You have 3 red and 3 white, and any red is out. You have 3 red and 3 white, so this is going to be 3 out of 6. I could have said 1 out of 2, which is the same thing. So now you can you get some cancellation here. 3 and 3 is 1 out of 2. 2 and 4 you get canceled, and one way or the other you do this algebra, you're going to have 2 out of 7. Okay? So this is calculation done by using properties of probability. Very easy. Okay? But you need to know this property. And you have to be familiar with that. Okay? Now, if we're going to do the counting, then the question becomes in how many ways I can get 2 balls out of the hat. Well, I have a 7 balls, and I can get the 2 balls out of the set of 7 by way of combinations. So again, I don't really care in which order. So I can get this white and this red, or I can get this red and this white. Is to me the same thing. Now, if you want to label the balls, then you're going to have to think about permutation. But all the way you have to think about permutation. But since I didn't label them, I just have a colors. To me, it's the same. So 7 chooses 2 permutation. 7 chooses 2 combinations is by the good old formula. I have the blah blah blah. and I have, I don't know, 21. Use your calculator. Don't believe me, but I think it's 21. And now the next question is, since I get two red balls, right? In how many ways I can get two red balls if I just choose two red balls? Well, I have 4 red balls. And if I want to choose red balls only, I can get that in this many different ways. So I can get, you can even count that. It's really not that hard. You can get this one and this one. You can get this one and this one. You can get this one and this one. That's 3. Then you can get this one and this one. Or you can get this one and this one. That's 5. And you can have this one and this one. That's 6. And the order doesn't matter. So when you say this one and this one, it's the same as if it's this one and this one, right? So it's really 6. And this, of course, it is. Guess what? 6. 4 chooses 2 combinations is 6. You can write this whole formula, get 4 factorial on the top and the bottom, how many you're choosing 2 factorial, how many you're not choosing 2 factorial, blah, blah, blah. Cancel everything out, that's 6, one way or the other. Okay, now the probability of both red. So now we are arguing this formula we had some time ago. Both ball red. We have 21 different possibilities to get 2 balls out of hat. Each one of them is equally likely. It doesn't make any difference. I'm going to get this white and this white, or I'm going to get this white and this red. If I'm not watching, I'm drawing that at random, it's equally likely. And I have 21 choices. And of course, in my event, to get both ball red, there are 6 different options to get 2 red. So you have to divide 6 with 21, and 1 cancellation, you get cancel this with 3, and you get 2, and you cancel, divide with 3, and you get 7. And guess what? Of course, turns out to be 2 out of 7. Right? So I am leaving now to you. The calculation is the same, right? Whether I'm using counting is not that difficult, or I'm going to use the property of probability, which is also not that difficult. It's not that long either way. So I'm leaving that to you to think, to find out that to get both balls white is going to be 1 out of 7. So think the same way, just numbers are different, of course. And you can calculate that by using properties of probability. You can use the efficient counting. And you will get 3 out of 21. If you do efficient counting, it's going to be 1 out of 7. So it's twice more likely to get 2 red balls than 2 white balls. But it's more than 50%. 4 out of 7 times is going to be 1 red and 1 white. And okay, I explained this 4 out of 7 down there. And of course, this ought to add up. 1 out of 7 plus 2 out of 7 plus 4 out of 7 is 7 out of 7. So it's going to happen. Either both are red, or both are white, or one is white and one is red. Okay? So you can see the power of the ability to calculate this by using properties of probability, which is sensible, and we use them all the time. You can also use the sufficient counting. Although in this particular case, the counting is not a big problem because it's 21 possibilities. You can even write the whole sample space down, but you have to agree to write it in some particular way. First, I don't know. It will be kind of messy, but you can do it. Right, so I'm done with this story here. I didn't do some of the problems over there about cards, and of course the Mississippi problem is really going to be difficult. I'm not going to bother you with that in the test. This is a little bit easier to understand in how many ways you can rearrange word summary. It's up to you whether you're going to read it or not. I'm not going to bother you with that either. But these card tricks are kind of interesting. So again, you can find this stuff on the internet. Just have to be careful where you're reading from, because some places, some people are writing complete nonsense. They don't really know how to find it, so they don't know how to explain it. So that's a problem. But if you get it from somebody who does mathematics or some professor or something like that, then you're probably going to get it right. It's kind of interesting thing to get it. So 1 pair of a kind I'm calculating this is 42% of the chance to get that, and it's about the same to get nothing at all. So this is like 84% chance to get either pair or nothing. And this is probably, you know that already if you play poker. This is the most often you get in a one dealing. It's rare to get anything better. And obviously, this story now ends. You have a pretty decent homework there to work on, and you might want to use that knowledge that you learned in this lesson. That's the homework on finite combinatorics. The next time I see you, we're going to be doing something new. All right? I'm going to end up